Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all in a new playlist, Introduction to Real Analysis by Robert G. Bartle. Although a separate playlist of real analysis is available at my channel, but in that playlist, uh, I am following the book Principles of Mathematical Analysis by Walter Rudin. In this playlist, I am particularly focused on lectures of real analysis from R.G. Bartle book. So today we are going to discuss our first lecture from this book, and here I am using the latest edition of this book. That is actually the fourth edition. So we will discuss from the first chapter, that is actually Preliminaries, and this chapter is actually the discuss some basic definitions, some symbols and notation that we will use throughout this book. So let us start from chapter number 1, Preliminaries. In this chapter, we will discuss, in this lecture, we will discuss here section number 1, sets and functions. So in today, that is actually the basic lecture, we will discuss some basic definitions. First definition is if an element x is in a set A, we write this as x belong to A. We say that x is a member of A, or that x belong to A. And if x is not in A, then we write this as like this. If every element of set A also belong to set B, we say that A is a subset of B, and we write A subset of B, or B is superset equal to A. We say that A is a proper subset of B if A is subset of B, but there is at least one element of B that is not in A. In this case, we write this as. In the first case, suppose our A is only 1, 2, 3, and our B is also this 3, 2, 1. Then in this case, you can say this is A subset of B, because every element of A is an element of B. But if your B is contain at least one element other than A, like 1, 2, 3, 4, 5, now in this case your A is proper subset of B. The next one definition is definition 1.1 that we will use also later. Two sets A and B are said to be equal, and we write A is equal to B if they have the same elements. Like this here, A and B both have the same elements, so they are equal sets. To prove A and B are equal, we must show that both are subsets of each other. That is, A is subset of B and B is subset of A. The next one is the way to represent a set. Representation of a set. Usually in some other context of real analysis, you can find that a set can be described by three ways. One is the descriptive way. One is the descriptive way. Second one is the set builder form, or second one is tabular form to represent a set, and the third one and the last one is a set builder notation or set builder form. So these are the three methods commonly we used to describe a set. But in this book we will discuss only the last two ways, that is the tabular and the set builder form. A set is normally defined by either listing its elements, that is actually the tabular form. In tabular form, you always represent a set by listing its. For example, when you say the set of first 5 natural number, then you can list it as 1, 2, 3, 4, 5. So this is the tabular form of the set of first 5 natural number. If you want to find its set builder form, you can write it as x belong to n such that x is less than or equal to 5. So this is the set builder form in which you are using some a property that specify the elements of that set. So we can read it as a set is normally defined by either listing its element explicitly or by specifying a property that determines the elements of the set. If P denotes the property that is meaningful and unambiguous for elements of set, then we write X belong to S P of X for the set of all elements X in S, for which the property P is true. If the set S is understood from the context, then it is often omitted in the notation. Further, uh, in this book, the author always used to represent when the author defines a new definition, then he always used this symbol, colon with equal sign, instead of just writing equal sign between two sides. For example, in order to define set of natural number, he is writing n with colon equal sign like this, 1 2 3 4 set of integers. Throughout the book, we will denote this as 0 plus minus 1 plus minus 2. Set of rational number is set of the form that can be written in set of the elements that can be written in m over n form, where m and n are integers and the denominator is non-zero. The set of real number is a union of rational and set of irrational number. We will discuss the set of real number in detail in chapter number 2. This is the first example available in your book. Actually, this is the set builder form of set. In this set, there is a quadratic equation whose roots are integers. The set x belong to n such that x square minus 3x plus 2 equal to 0 consists of those natural numbers satisfied in the equation. Since the only solution of this quadratic equation are x is equal to 1 and x is equal to 2, we can denote this set more simply by this. So actually, the above one, this is the actually set builder form that is actually using here. This shows all those integers, all those roots that are just integers and satisfying this condition, while this is the tabular form of those roots. Further, the second one is the author says that every natural number n is even if it can be written as n is equal to 2k. The set of the even natural number can be written in this form 2k such that k belong to n. Similarly, which is less cumbersome then to write n belong to n is equal to 2k, k is equal to n. This mean to say this is the simple and easier way to write of writing set of natural number rather than this. Similarly, the set of odd natural number can be written as this. The further next one is set operations. You can usually on a sets we can define union, intersection, and complements. In set theory, the word or correspond to the union, while and correspond to the intersection. For example, when we say A or B, this shows A union B, and when we say A and B, this is referred to A intersection B. So we can define the following operations like this. A union B is set of all those elements that consist on X belong to A or X belong to B. In case of intersection, X is elements of both sets, should be elements of both sets, X belong to A and X belong to B. The next one is the definition of the difference of two sets that in other contexts you can find it as A minus B. This is A minus B. Difference of A and B. This is A minus B. But in this book, this is like as the complement of B relative to A is denoted by A backslash B. This consists on all those elements of A that are not elements of B. These three operations can be looked in this figure like as this. This is the first figure in which there are two sets A and B, and both the sets are shaded by gray color. So in case of union, we will always shade both sets, these like this. In case of intersection, the only common part is shaded here by the black lines. This area shows a intersection B. While in case of A minus B or complement of B relative to A is denoted by this brown area with black dots here. The brown shaded area is A, complement of B relative to A, or simply A minus B here. The next one, the set has a no element is called empty set and denoted by phi. Two sets A and B are said to be disjoint if they have a no elements in common. This can be expressing as A intersection B's empty sets. Now, the next one is important segment of today's lecture. How can we prove two sets, equality of two sets? So, for elaboration, we are discussing here De Morgan law for three sets. I hope you are familiar about De Morgan law for two sets like this. You know, A intersection B complement is equal to A complement union B complement. Because when we apply complement, then complement convert intersection to union, and if we apply complement in case of union, then union is converted to intersection. This is the intersection of complement of two sets. But in this book we are going to discuss De Morgan law for three sets. So these are the two parts of De Morgan law for three sets. I am discussing here only the first part, and the second one is for your exercise. In the first part, we need to show that this shows, what does this show? This shows complement of B union C relative to A, or simply if we write it as A minus B union C is equal to A minus B intersection A minus C. So how we will prove this? To prove this, I will use the method. I will take some arbitrary element x from any side. Suppose I take here x x is an element of left side A dash B union C. Then I will show x is also element of the right side, that is x also belong to A intersection this. And conversely, I will again show if x is element of the right side, then x is also element of the left side. So to prove A, we will show that every element in this set is contained in both on the right side, because on the right side here are the two sets. So I will show when x is an element of this set, then x is element of the right side, x is also element of this set, and this set consists on actually in two parts. So that's why I am writing here is contained in both A minus B and A minus C. And conversely, if x is element of this part, what does this part show? This part shows the complement of B union C relative to A. This is the difference of A minus B union C. So this shows that x is in A but x is not in B union C. Remember, you know, when you say x belong to complement of B to A, it means x is an element of this part, x belong to this part but not in this part. So similarly, when you say x is element of this part, this shows that x is in A but x is not in the union. When x is not in the union of two sets, it means x is neither a part of B nor a part of C. Therefore, x is in A but not in B, and similarly x in A but not in C. So this can be written as x belong to A minus B and x belong to A minus C, which shows that x is an element of both sets. X is elements of this and x is an element of this. This shows that x is in the intersection of this set. Next one. Conversely, we take x belong to this element, this part, and we will show that x is element of the also element of the left side, this. When x belong to the intersection, this is intersection. So according to definition of intersection, X will be the element of the first set and X is also element of the second part. When X belong to this part, what this part shows, this shows that X belong to A, but X does not belong to B. Similarly, when X belong to this part, what this part shows X belong to A, but X does not belong to C. This implies X is an element of A in both cases, but X is not element of B and X is not element of C. This shows that X cannot be element of a union of B union C. X cannot be in the union of B union C here. This shows if X is in A but X is not in B union C, this shows that X belong to complement of B union C relative to A. I mean to say X is an element of A minus B union C. But X was arbitrary element of this set. X was element of this set. This shows that since the set this and this contain the same element, they are equal by definition. So let us discuss the remaining part of the lecture after prayer. Okay. Next we move towards the important concept of the subject, that is function. In order to discuss function, firstly we define what is the Cartesian product of two sets. If A and B are two non-empty sets, then their Cartesian product is denoted by A cross B, and it is the set of all order pairs such that the first element of order pair belong to first set A and the second element belong to set B. For example, if A is equal to 1, 2, 3 and your set B is 1, 5, then their Cartesian product A cross B is the set whose elements are the order pairs 1, 1, that is by combining the first element 1 with first element of B 1, then again by combining 1 with 5, and similarly you can combine other elements 2, 1, 2, 5, 3, 1, 3, 5. So these are the 6 order pairs. Here you can check number of elements in A are 3 and number of elements in B are 2. So the number of elements in A cross B will be 6 simply. The next one, this figure shows if your set A and B are finite sets or discrete sets, then their Cartesian product is just the points in the plane. Like as in the given example, A is 1, 2, 3 and B is 1, 5. Their Cartesian product consists of the 6 elements. So if you plot these 6 order pair in Cartesian plane, suppose this is x-axis, this is origin, this is your y-axis. Now if you draw or if you plot these the order pair, then these order pairs just simply represent a point. Like as the first order pair is 1, 1, suppose this is x is equal to 1 and this is y is equal to 1. This point shows the order pair 1, 1. Similarly, suppose this is x is equal to 2, then this point represent order pair 2, 1. Similarly, you can plot all other points. Suppose this height represent y is equal to 5 and this is x is equal to 1, then this is the point x1 y5. So in case of so this figure says that the order pair, if your set A and B both are finite sets, then their Cartesian product is just points in the plane. But if your set A and B are in the form of the intervals, then their Cartesian product is always form a rectangle. For example, consider here your set A is a closed interval 1 less than or equal to x, x less than or equal to 2. So this portion represent the values of x lies between 1 and 2, while this height represent the values of y, that is here 0 less than or equal to y less than or equal to 1. So in this case, if you find when your a is the closed interval, when your a is closed interval 1 say 2, and your b is the closed interval 0 to 1, then in this case when you will find their Cartesian product a cross b, this will always represent this rectangle. Now if your set b is here set b consists on two intervals of y. If your b is 2 to 3, then while set a is remain same, now it will again represent a rectangle, but the height of this rectangle will here when y lies between 2 to 3. So in short words, when your set a and b both are in form of closed interval, then their Cartesian product always represent a rectangle in the xy plane, while in case of finite sets, mean to say when your set consists on points that are countable, uh, then their Cartesian product is always in form of these like these points in the xy plane. Next we define the proper definition of the function. A function f from set A into set B is a rule of correspondence that assigns to each element x in A there is a uniquely determined elements f of x in B. What does this definition says? This says that if for every x belong to A, there exists f of x belong to B, and this f of x is unique, mean to say for each x there is a unique f of x, then such correspondence, such rule of correspondence represent a function. Diagrammatically you can see this as, suppose this is your set A and this is your set B, and this is the rule f. Suppose there are here some elements in A, that is x1, x2, x3. When you apply f on x1, then the elements in B corresponding to x1 is f of x1. Here f of x1 represent value of f at x1. Here f of x1 does not represent the function, it just represents the value of f function f at x is equal to 1. Similarly, if when you apply f on x2, the corresponding value is f of x2. Then if such type of correspondence exists, then we say this f is a function. But on the other hand, if you see look like this, suppose this is x1, this is x2, this is f of x1 and this is f of x2. Suppose when you apply f on x1, you get two values and both are attached with x1, mean to say at x1 when you apply f, it gives f of x1 and f of x2, then such correspondence according to the definition is not a function. Algebraically you can understand this by a simple example. Suppose your y square is equal to x. Whether this represent a function? Not, because when you put a single value of x here, suppose you take x is equal to 1 here, this implies y square is equal to 1. By taking square root on both sides, we have y is equal to plus minus 1. So when x is equal to 1, you obtain two values of y. This relation, this correspondence, according to this definition, is not a function. While if your y is equal to x square, when you put x is equal to 1, this implies your y is equal to 1. For a single value of x, there is a single value of y. This represents a function here. So this gives us the definition of function algebraically. Next definition of function is also available in this book, but this is a set theoretic definition. This is a set theoretic definition. This definition says, let A and B be the two sets. The function f from A to B is a set f of order pair A cross B. I hope you know from your previous classes, a function f is always a subset of Cartesian product A cross B when we define function in form of set theory. That's why the author is saying that then the function f is a set f of order pair A cross B such that small a is belong to the set A. For each x A belong to A, there exists a unique B belong to B with order pair A B belong to F. The set A of first elements of function is called domain of f, and it is often denoted by d of df. The set of all second elements in f is called range of f and is often denoted by rf. The notation f such that A to B is often used to indicate f is a function from A into B. We will also say that f is a mapping of f into B, or that f maps A into B. If AB is an element of f, it is customary to write B is equal to f of A, or sometimes A maps to B. This is also another notation that we will use in this book. This is the image that represent one of the important concept here. If B is equal to f of A, we often refer to B as the value of f at A, or it is called image of A under f. Note that although domain of f is always denoted by A, we only have a range of f is always subset of B. This is important. Actually, when you define a function from set A to set B, this is possible that there exist some elements, some extra elements are present in set B. So actually set B is called codomain. This set is called codomain, but the range of f consists on all those elements which are the images of A under f. Range of f represent set of all images under f. B is called codomain. That's why range of f is always subset of B, because it is possible that B contains some extra elements that are not the images of f. From this figure you can notice that the height of B, this represents set B. The height of B is bigger than the height of range of f. Your range of f lies in this interval, while your set B is at this height. The last one, vertical line test. This is actually a geometrical tool to test whether a given graph is a graph of function or not. This test says that in a geometrical term, it says every vertical line x is equal to A with A is equal to A belong to A intersect the graph of f exactly 1. What does this say? Suppose we have semicircle. According to vertical line test, if every vertical line cut this graph exactly at one point, if you draw this first vertical line, this cut the graph at this point only, that is exactly 1. Again you draw a vertical line, this vertical line also cut the graph exactly at one point. So this semicircle is a graph of a function, is graph of a certain function. This is a graph of certain function. But on the other hand, if we have a full circle, lies in four quadrants. Whether this represent a graph, represent a function or not? No. According to vertical line test, if you draw a vertical line, this vertical line cuts the circle at 2 points, at this point and this point. Similarly, if you draw this vertical line, again this vertical line cuts the graph at 2 points. If you draw this vertical line, this also cuts the graph at this point. So in the domain of this graph, from this point to from this point, whenever you draw a vertical line, every vertical line cuts the graph exactly at 2 points. So this circle is not a graph of function. Is not a graph of function, or simply it is not a function. Not a graph of function. Not a graph of function. Similarly, if you draw a random graph like this, suppose this is my first another graph. Again, if you draw a vertical line, this vertical line cuts the graph at multiple points, at this point, at this 3, 4, at 5 points, 6 points. At 6 points this vertical line cuts the graph. So this is not a graph of function. In the last paragraph, that is a transformation and a machine. In this paragraph, the author wants to say that the two important things. The one important thing is that uh, function a function is like as a machine. A function is like as a machine. Suppose this is a grinder machine or a juicer machine. When you give any input to this machine, suppose your input is x. Your input is x. When you give an input x into this machine, your machine, that is here actually f. Lastly, you can put only those objects in this machine which are grandable or which are suitable for these machines. For example, if this is a juicer machine or a grinder machine, can you give input of stone or iron to this machine? No. Uh, you cannot give this input because these are not grandable. So similarly in mathematics, if your function f is like as machine here, so you can put only those values of x, those input of x values in this machine which are belong to the domain of f, which is clearly if we try to insert something that does not belong to domain of f into f, we find that it is not accepted for f. For f can operate only on those elements for domain of f. So in the last paragraph, the last visualization makes clear the distinction between f and f of x. The second things in this paragraph that is important, that may be confusing point for students according to the author. Author wants to say that the first thing, this represent a function, and f of x, this represent value of function at x. Value of function at x. So I hope today's lecture is helpful for you. If you find my lecture helpful, then kindly like, share them. Okay, see you in the next lecture. Take care. Allah Hafiz.